Okay, so let's look at a few more examples that are, applying the first derivative test. And like one of the questions that you're almost guaranteed to be asked several times, whether it's a free response or multiple choice, is analyzing a function given its derivative graph, which we have here in example 3. And you have to remember that the behavior of what you see, like, right, what I'm visually seeing is the derivative, not the function itself. And when you first start, solving these problems, it's really easy to like be tricked by what you see versus what you're trying to answer. So just again, this is the derivative. So the derivative represents, is the function increasing or is the function decreasing? So, a lot of times, especially when I first start doing these problems, somehow indicating this x-axis here, that's a key place to be looking, because anything that is above the x-axis would be a positive first derivative, meaning your function is increasing. Anything that's below the x-axis would indicate that it's a negative derivative, therefore the function is decreasing. And when you're visualizing this derivative, right, you're given the derivative, you need to make reference that it's the derivative you're analyzing. So let's take a look. It says, when is the function increasing? So the function is increasing anytime your first derivative is positive. So visually, I'm seeing from about, looks like -6 to -3. So -6 is less than x is less than -3. It looks like 0 to 3. And then here's that sort of like, well, it's 0 for an instant, but it continues to increase. So I could just combine that and saying, or x is greater than 0, right? Because it'll include everything. Or if you wanted to, you could say 0 is less than x is less than 3, union 3 is less than x is less than infinity. Like, that's fine too. But most likely you'd see it like that, because technically you are still increasing. When is it decreasing? Well, from -6 and to negative infinity. So you could say x is less than -6, and you could say, or between -5 and 0. Now, this is just an inequality. You could also use interval notation. Now, here's the part that I really like to make sure that you know how to do. Identify the extrema, right? Remember, to be an extrema, you're a critical value. Critical values are where the derivative is 0 or it does not exist. So where are the 0 derivatives? Right along where I circle or highlighted the yellow. So I'm going to start at -6, because look what's happening at -6. Your derivative went from a negative value to a positive value. Right? So if your derivative goes from a negative to a positive, that means you're a local minimum. So I would say, like, x equals -6. There's a minimum, and I know that because your derivative, because that's what I physically can see, right? F prime. So derivative changes from negative to a positive. Now, are there other places where it changes from negative to a positive? Yes, there are. Well, there's one, right? Right at 0. 0, we went from a negative, right? Think about it's below the x-axis, to above the x-axis, negative to positive. So it's a minimum. So I could say x equals 0. It's another minimum. And remember, when I'm saying the word minimum, it's a relative minimum, could be global, but it's relative. And it's just identifying when the function has the minimum. It doesn't say what that minimum is. You'd have to then substitute that back into your original function. And I could say f prime changes from negative to positive. Okay. Now let's talk about -3. Your derivative changed from positive to negative. So if you change from positive to negative, you're a local maximum. So I know that at x equals -3, the function has a max. And how do I know that? The derivative, right, related to what you physically can see. I'm seeing the derivative graph. So the derivative changes from positive to negative. And feel free to use those pluses and minuses in your free response. It's perfectly fine to do that. Now, does it change anywhere else from positive to negative? No, it does not. There's a suspicious point here, right? At x equals 3, that's suspicious. The derivative is 0, but it doesn't change signs. And remember, we said being 0 is not good enough. So I could make a little note that says, note x equals positive 3 is a saddle point. It's not a max or a min. X equals 3 is a saddle point. And then, so I would say like not a max or a min. So it's not an extrema. And remember, a saddle point would represent, kind of foreshadowing into the second derivative test is going to represent a change in curvature. Now, assuming that this went on forever, that's it. But let's say this was a definite ending point. And let's say that this was a definite ending point. Then I would identify this as being a max or a min. And think about like this is beginning a negative derivative, right? It's beginning an interval that's below the x-axis. So if you begin a negative interval, if you begin a decreasing interval, you're actually a max. And that's so visually deceiving because it appears that I'm looking at something that's a low point on the graph, which I am. But it doesn't matter because that's the graph of the derivative. I want to know what's the function doing. If this begins a negative derivative, right? So if you begin a negative derivative, that means you were a maximum. So I could identify, let's say that's like negative, let's say 6.25 or something like that. So negative 6.25, I'm also going to say is a maximum. And how do I know that? Because we begin a decreasing interval. And this is like the one time you could use the word it. So, or you say beginning of a decreasing interval. Beginning of decreasing interval. Now, let's look at the other end. Up here, that's the end of an increasing interval. So if you end at the top, you're also a maximum. So then I could also say, and I'm just estimating that's about 4. It's almost exactly 4.5, but again, my eyes are bad, so maybe it's not quite exact, but I'll call it x equals 4.5 is another max. And how do I know? Because it's the end of an increasing interval. Okay, excellent. But really, really important to emphasize are those identifications and their justifications. Okay, I think there's one more. Same idea. Oh, I'm sorry. I realized when is the second derivative equal to 0? So the second derivative would be the derivative of this graph. So when is this 0? So the second derivative is 0 here at that peak, here at the trough, here at this peak, and here at this trough right there. So those are the 4 points whose second derivative of the function is 0. And since we are already looking at the first derivative, we just need to look at the slope of the tangent line of this graph. So it looks like at -5, it's at about negative 2. I'll call it 2.5, probably, or sorry, not negative 2.5, call it like negative 1.5-ish. And then like up here, like it maybe like at 1.1, and they're at 3. So we'll call it -5. We said about negative, it's probably closer to like negative 1.6 at about 1.1, and then also at 3. Okay, but now we want to do the exact same set of questions here. And, the ones that I'm really going to focus on are the relative mins and maxes. So let's start here. Let's say that that's a definite endpoint, and this is a definite endpoint. So this right here is at a max or a min. Well, it begins an increasing interval because everything that's above here has a positive derivative value, and everything below here has a negative derivative value. So you're beginning an increasing derivative. So if you begin increasing, then you would have started as a min. And again, so visually deceptive because I'm seeing it as the highest point. Doesn't matter. It represents the derivative of something I can't see. So that is negative 3 point, let's say 2.5, or let's say negative 3.3 is a minimum. How do I know? It begins an increasing interval. begins increasing interval. And again, you might be visually deceived because you might say, well, wait a minute, it's going down. Yeah, the derivative's going down, but because all of this is above the x-axis and this represents the derivative, then these y values all represent positive slopes. So the function that we can't see is going up. All right, so then let's go to the next one. Right here at -3. Think about what's happening there. That's going to be a maximum because your derivative changed from positive to negative. So f prime of x changes from positive to negative. Okay. 0, suspicious, right? Because its derivative is 0, but it's neither a max nor a min. It's neither. It's a saddle point. I promise you that's the last bell that's going to go off in this video. It's a saddle point. So because remember, we're negative, so we're decreasing. We pause for a moment, and then we decrease some more. And if you want to know, well, what would that look like on a potential function? What would that have been? But think about an upside down cubic function. You're decreasing, you're 0 for an instant, and then you continue to decrease. Okay, and then we have a value right here at 4. Your derivative did change from negative to positive. So when you do change from negative to positive, you are a minimum. Okay, so I was pausing to hopefully that you were able to fill that in. Okay, so x equals 4 is a min. And again, we know that because the derivative, so what I physically can see is changing from negative to positive. And this is the reason you're going to use for all of them. So once you know what to say, then it's become very efficient in your response. And then let's look at the very last thing here. You're ending on a positive interval. You're ending on a decreasing value. So you know that at x equals 4 point, let's say, call it 4.1 or 4.2, you're a max. And how do you know? Because you're at the end, or it ends an increasing interval. So again, just speaking from experience of teaching this, that often students, it's easy for them to get mixed up. And I can guarantee the AP exam will try to intentionally, deceive you based on what is it you're looking at versus what are you being asked. And that means Mr. Brown will kick it up 3 times as much to try to make it deceiving. Only because I'm testing, do you understand what's happening? You're analyzing a derivative, so but in order to you're analyzing the derivative in order to answer something about a function which you don't even see. Okay, so big topic. Almost every free response question, almost every year, there's a free response question that deals with this idea of increasing and looking at a first derivative test, but then also when we look at next week, second derivative tests and what those represent with curvature.